Hello again and welcome. You can see I have a new meter we're going to be looking at. This is produced by Sun. The company is also listed as eSun and AllSun. This is a part number EM135, made in China. You wonder what this has to do with the motorcycle? I've had a few people asking me about automotive meters. That's exactly what this meter is. We can see digital automotive meter. So this has some features that make it unique for automotive use. It says besides the AC and DC voltage, AC-DC current, this meter can also be used to measure RPM, dwell angle, fuel injection duration, O2 sensor, alternator, and for fault code detection. Just looking at their website, they show a picture of it measuring the RPM. They have a small clamp that they attach to the plug wire. Here they show the clamp. Here they show connecting it to the coil, and they're measuring the dwell time. If you're not familiar with dwell, that's essentially when the coil is being charged. Here we're looking at a fuel injector, and they're measuring the time that it's active for. Here they're looking at the on-off of a O2 sensor. This would not be a wideband type. I'm doing some kind of a test with an alternator, looking at the fault codes, measuring the diode. This one's pretty funny here. See, they're measuring the AC current, but if you look at the photo, it's looking at 233 volts, and it's measuring directly across their AC line. So they're not actually looking at AC current. They're measuring AC voltage, and this is not what you would want to do to measure your AC current anyway. So they say it's a 5-digit LCD with a max reading of 99,999. Looks like our sampling rate is 2 to 4 times per second. You can see it looks like it comes with the clamp, set of probes, some alligator clips, a temperature probe, and with the batteries and a user's manual. But you'll notice on the web page they don't actually have this manual available. I looked for it before I purchased the meter, and I could not find this manual anywhere, which is kind of unfortunate. You can see it comes in a nice carrying pouch. Plenty of room, I would say. We have a manual. There's the temperature probe for it. The material on this is quite thick. The leads are marked RU AWM 1803 VW-1 80 degrees C. Then it has a part number E301305 2000 volt 18 gauge Hurwell. The tips aren't especially sharp. I guess for automotive you wouldn't care. It's kind of a unique design. You can see it kind of has a triangle finger grip molded into it. Looks like it comes with a couple of alligator clips. I don't see 4 like what the picture shows. It's not a real good fit. I don't like these ones that just press on. I'd rather have the screw-on type. Cost on this meter is about $100, so I'd expect a little better probes with it. You notice the one thing we're not seeing in this is the inductive pickup. Looks like they might have had a place for it up here. I don't know if they just left it out, or maybe that's sold as a separate piece. Again, the online web page doesn't really tell you what's all included. There's a couple of things looking through this manual. One, they never mention the company who produces the meter. Another thing I notice is there's no mention of any kind of warranty. Basically, with it coming out of China, you know you're not going to get a warranty anyway, or it'd be very difficult to get one. Here we can see it has a 400 millivolt range up to a 600 volt range. So the lowest resolution is 100 microvolts, and it's only 1% plus 5 counts. Look at the input impedance, 840 k ohms. So it's not like a typical meter. For AC voltage, it's very similar. It's 100 microvolt resolution, 1.5% accuracy plus 5 counts. So again, 840 k ohm input impedance. Frequency range 400 Hertz. Again, with this meter being targeted for automotive and not electronics, it's not really important that it measures down into the microvolt range. We can see on the 4 amp range it has a resolution of 1 milliamp. And again, the accuracy on the 20 amp range is 1.5% plus 3 counts. On the AC current, you can see it's 2.5% plus 5 counts. And again, the frequency range is shown at 400 Hertz. You can see the ranges for resistance. It's got 404K, 40K, up to 40 meg. Again, the specs aren't all that great. It does have a diode check. Looks like the open circuit voltage is 1.5 volts, so not very good. For continuity, it looks like they show when the resistance drops below 30 ohms. That's when the buzzer will enable. I don't know why they have a capacitance check on the meter. I've never had a need for that in automotive, but looks like it can read up to 100 microfarads. Frequency isn't all that great, 20 kilohertz. Temperature, looks like it can read up to 1000 degrees C and down to -20. Again, not that great. Here we can see the fuel injection duration. So 50 microseconds up to 250 milliseconds with a 10 microsecond resolution. And notice the accuracy is plus or minus 50 microseconds plus 2. The input voltage range is approximately 0.8 volts peak to 50 volts peak. Maximum allowable engine RPM is 20,000. Here we can see the tach function. Again, 1 to 12 cylinders. For a 2-stroke engine, they're shown between 60 and 10,000 RPM. And for a 4-stroke, of course, it's going to be double that. And it has a resolution of 1 RPM. Notice in the back though, page 50, it says it comes with a manual, test leads, 1 pair, and inductive pickup. Looks like it's included, 1 piece. So yeah, for whatever reason, we didn't receive ours with this meter. It's not going to prevent us, I don't think, from doing a review on it, but just be aware. Again, the cost for this meter ranges between about $90 and $110, depending on where you get it from. You can see it's all sealed. I'm assuming it does not come with batteries. Does not appear to. It's quite heavy for not having the batteries in it. The case is fairly large. Let's go ahead and we'll put some batteries in this and let's see if it'll power up. See, there's not a whole lot of information on the back. You can see it powers up just fine. It's got a nice looking display. See, it has an off on both sides of the meter. I don't believe this meter was independently certified. You can see it just shows the CE mark. Automotive tester. Notice in the upper right here though it says Cat 2 Max 600 volts. You know, normally with these Chinese meters they're always showing Cat 3 600. It's rare you see a Cat 2. Let me just pop the cover on and we'll try a basic functional test with it. You can see how far down the banana connectors are. See, these will actually fit down inside there. I think that's a pretty good design. I think they do that for mechanical strain relief. Yeah, I mean, these are going nowhere. You'd want something like that for automotive use. Alright, we'll just start with our 5 volts. You can see it's pretty much dead on. This should be roughly 2.5. Looks good. Let's try it in AC volt mode. I don't think this is an RMS meter. Reason I say that is this should read 2.5 volts right here. Let's just have a look with the Bryman. You can see how far this is off. So 2.77 versus 2.48. The Bryman is actually reading what I would expect coming out of this box. And again, if we take pi over the square root of 8 or 1.1107, multiply that by 2.4, You can see we get 2.776, and that's pretty much what this EM135 is reading. So yeah, this is not a true RMS meter. You know, again, for the $100 or so that you're going to spend on this meter, you'd expect it to have RMS, but you know, normally you're working with DC voltages in automotive, so they must not have thought that that was a big problem. So let's go to the 115 millivolts. Again, reading a little high. I would expect that. This should be roughly 70 volts AC. You can see that's reading pretty close. So let's just try frequency. Again, this is AC coupled, so we have a zero crossing. And this is a DC coupled input. It's not having any trouble with that. This will be 30 Hertz, 15, and 120. This will be resistance mode, so here's with a short. Looks good. It's with 50 ohms. You can see how long this thing takes to settle in. Quite a bit of time. Let's try the 100 ohm. It's with a 1K ohm. Say 10K ohm. This is a 100K. Again, most of these resistors are better than 1%. This is a 1 mega ohm. And this is with a 10 mega ohm. Let's just try the 40 mega ohms. No problems there. Let's just try it up at 100. This should overrange it. It does. This is diode check mode, and again, this is with a short. And they said the open circuit voltage on this was 1.5. Let's just see if that's true. Looks like 1.8 volts for open circuit. So here's with a single diode. Looks fine. Two diodes. It reads an open. It's kind of a shame. I'd think for automotive you could at least do two diodes in series. Let's just see if it'll light up our LED. Of course it can't. It's continuity test. Quite fast. Latching type. Let's try temperature. And this should be roughly 500 degrees Celsius. Looks pretty good. Should be room temp. That looks fine, and a little over 1,000 degrees. So let's just see where it overranges at. Looks like about 1,006 or so. That's our ambient temperature in the upper right, so 22.5 degrees C. Of course, it can read in Fahrenheit as well. Alright, for current, I've just got the 2 meters in series, and they're connected up to my bench power supply. You can see they're both reading about 30 milliamps right now. It's the upper limit of my power supply. You can see both meters are basically reading the same value. To use the TAC input, you can see it goes between the two far left connectors. It's kind of interesting because you're going to flip it, so this becomes the common now, where like when you're looking at the current, this is the common point, and the positive side is the one that's marked RPM. Alright, so this box can put out a 60 Hertz waveform. So if we did 60 squared, that would be 3600, and then depending on the mode, if it's in 2 or 4 stroke mode, I would expect we're going to get either 36 or probably 7200. And so 7200 RPM. So we should be able to change it to a 2-stroke. That's the button on the right. You can see 2 and 4. So there's a 2-stroke, so 3600. So when you're working on a car, they can be quite noisy. So you see we have this input right here. This is setting the trigger level. So if we turn this thing all the way up, let's see if it'll still trigger. Yeah, it does not. Again, we go to the lowest res. It seems to have no trouble with it. At the RPM, you can see input voltage must be between 0.8 volts and 50 volts. Polarity must be correct, otherwise it's impossible to make the measurement. You notice that you can do a dual display, so we can have 4 leads attached to this, and we can be looking at the RPM in the upper right, and we could be looking at voltage in the lower main display. So if I switch this to voltage and I enable our RPM, you can see the upper right, it's 3597, and then I'm free to use the other inputs. So that's kind of a nice feature. For frequency dwell angle, fuel injection duration, for level 1 it's 0.8 volts, and then that's 3 volts for the RPM function. The level 2, it takes all the way up to 4.5, and then 6.1, and then 8.1 volts. So they have a fairly fine resolution here for setting up the RPM. You know, again, that's very helpful if you're working in a noisy environment like with an automotive ignition. I would expect this isn't going to trigger on anything but level 1 using this box, and that seems to be the case. See, the meter also has a dwell angle and time function. Select that here, and in dwell mode we can select the number of cylinders. That's done through the range, so you can see it's set for a 4-cylinder. If I push it again, see, it'll go up to a 12 and then goes back to a 1, works its way through. And when you run this mode, use the other set of leads. What we can do is put the two here in parallel, and I should be able to read both the RPM as well as the dwell time. Let's just try it with a single cylinder engine. Make the math a little easier. It should be 50% duty cycle, so half of 360 or 180 degrees. So let's just try it with a 2-stroke, and that should remain 180. That seems to be the case. So if we go to a 2-cylinder, that should be 90 degrees, and back to our 4-cylinder, 45 degrees. So it's kind of nice. You can see the split display, so we're using the one set of leads to look at the tach and the other to look at the dwell. We can also get this in percentage, so 50% duty cycle, that would be correct. Let's see, the right, it also has our millisecond timer. Again, this is for looking at things like an injector pulse. So if we set this to 60 Hertz, that would be 8.3, I think, milliseconds for a half cycle. So we go to milliseconds, and yeah, 8.3 milliseconds. And again, I should be able to select duty cycle, 50%, that would be correct. Alright, you can see I'm putting out 1 volt AC. This is a sine wave, and it's attached to our RF generator. Currently this is at 60 Hertz. You can see it here. What I'm going to do is just slowly increase the frequency, and let's just see what the 3 dB point is for this meter. Again, they don't call it out specifically, but they talk about a 400 Hertz frequency range. See, it's already starting to roll off. This is at 500 Hertz. And we're at 7.8 kilohertz. So yeah, just slightly over 7 kilohertz is the 3 dB point. But for working in automotive, I could see a reason to actually have it this low. Again, that's a fairly noisy environment. So as long as we have this thing attached, let's just go to frequency. Let's see how high we can read with this thing. So again, this is 7.8 kilohertz. It's very slow. Let's take it up one again to 30. Well, it takes a long time to figure this out. Oh, and that's the end of it too, so that's 31 kilohertz right there. Let's see if we can change the range on it. Nope, you cannot. So they limit it at 30 kilohertz. And again, the manual talks about 20 kilohertz maximum. So at least it reads higher than what the manual states. You know, if they had actually had this manual online, I probably wouldn't have purchased this particular meter. it would have just taken a quick glance through here and I would have decided that nope. So again, for them making sales, it's probably better if they don't supply that additional information. Alright, this will be capacitance mode. Let's just start with zeroing it out. This will be 150 picofarads. This will be 1 nanofarad. Looks pretty good. 104. This is a 0.1 microfarad. Looks real good. This is a 1 microfarad. Looks real good. This is a 10 microfarad. Looks good. And this is 100 microfarads. Let's try turning off the rel. This is looking in the manual. You can see it supports up to 100 microfarads. It must just be on the edge of not being able to read this. What I'm going to do is demonstrate the alternator test. See that in the manual here. They're basically looking across the battery right at the output of the alternator. And it looks like they're looking at the ripple voltage. And you can see it says if the secondary display reads 0.45 volts or less, it means the alternator and associated rectifier diodes are in good condition. And then good is displayed. So currently I have the 2 meters in parallel. You can see the EM135 is in the AC mode and it's displaying roughly 0.69 volts, and you can see that compared to the Bryman in the upper right, this is 0.71 volts. So if I select DC, you can see both meters basically read the same, 20 volts on each. So we'll go ahead and select the alternator input. What's kind of interesting with this is you can see the ripple is 5 millivolts. And I would have thought that that would have been 750 millivolts. You can see the meter definitely adds some additional load. We're all the way down at 15. So all I have to simulate this is a function generator. It has a series resistance that goes through a bridge rectifier. And then the output of the bridge rectifier goes to a small capacitor. And directly across that capacitor is a resistor. So I'm just using this decade box here to trim the resistance to increase the amount of ripple. So I don't know really what these two numbers mean. You can see we're up at 350 millivolts right now and it's still displaying good, and compare that with still 790 millivolts of AC on the Bryman. So here we can see we're at 440 millivolts. Compare that with 800 on the Bryman. So as I continue to load this down, of course the DC bias is being reduced as well. And right there it trips out at 463. So the function seems to work. Again, I don't know what this number here actually means, but I would say that you could probably do just as good a job using a standard AC DC meter, just checking the two different independent values. Of course you'd have to have some kind of idea what you were looking for, and that would take experience. I think with this meter they're trying to take some of that guesswork out of it. So here I have my Bryman BM869S on the right and the EM135 on the left. The two meters are connected in parallel. I have them set to manual ranging, and you can see I'm outputting a 0 to 4 volt peak signal. And what I'm going to do now is just slowly increase the frequency, and we can watch the response time of the bar graph. Unfortunately with this meter it looks like the bar graph only updates when the display is updated. So this is currently at 50 millihertz. This is with 100 millihertz. Just manually adjusted the peak amplitude so this wouldn't change ranges on us. This is 200 millihertz. This is with 1 hertz applied. So unfortunately with this meter, if you're working with a signal that's moving very quickly, The bar graph on this is not going to be very helpful. You can see to the left I have our high voltage power supply. The Brightman is in parallel with the EM135. So what we're going to do is apply a AC 60 Hz square wave to this. And you can see it's reading 540 volts roughly. Let's select this to AC. Oh, again, I believe that's because this is an averaging meter. Unfortunately, I can't adjust the amplitude of our power supply when I'm running in AC mode. I think this is one of the first meters I've looked at that couldn't actually read this kind of voltage. So what I've done is I've just changed the strapping on the supply. We'll just run it single-ended. So let's see what we get. So 260 volts it looks like versus 232. And again, 1.11 times 232 should give us 257. Huh. What's up with that? Wow. Alright, it's fine here. 13 volts. Really? I think this thing's having an issue with that little bit of voltage going into it. Huh. Yeah, the meter was still working. It was just the display that was turning off. It's almost like it was rebooting or resetting or something. Right there it goes. Huh. Look at this. It's rock solid. Connect up a little bit of input voltage. Go to AC. Nothing there. Again, we'll crank this thing up a little bit. Seems fine. Again, we'll start getting up to that 257. Huh. I don't know what's triggering it. It definitely seems to be voltage related right there. See, it's still running. Huh. Well, that's pretty crappy. That's the upper limit of our power supply right there, so 547 volts. Again, if you took 1.11 times 489, this is roughly what you're going to end up with. And so already reliability seems to be an issue with this. Doesn't seem to be like a loose contact in the switch at all. It's not like flexing the meter causes any problems as well. It only seems to do it at the higher voltages. You can see on the back side they have a decal. It's covering up a CE mark apparently. It's molded into the case. It's a little different. They're using a little harness to attach the battery pack to it instead of spring clips like you would normally see. Circuit board itself looks pretty clean. It's quite the slice they've got going up there. This is the FS9721 LP3. Up here this is a Holtec part. So this would be our LCD controller, and this is the meter's front end. This looks similar to the TPI meter that I looked at and how they designed it. They had a separate front end controller. Under here you can see another QFP. That's probably their microcontroller. This is our Fortune FS9721 LP3. Again, 4,000 count meter. It's interesting because, you know, they made a big deal about how many digits this display was, and it's basically 100,000 counts. And you know, they never mention in that sheet that it's actually a 4,000 count meter. Again, it's kind of deceptive. I don't know why they just didn't put the manual online. That and the fact that we didn't receive the inductive pickup with it. Yeah, not too impressed with this meter so far. This is the Holtec part. It's the HT1622. And again, we can see this is the LCD controller. See a small mezzanine board. This is a Holley. It's a 20 amp. And it's rated for a brake current of 80 kA. What you don't see is there are no MOVs. You can see they've got a few slits in the board. There's 3 PTCs. These two are tied to the main input here. This is probably for the RPM input. They just have their series resistors here for the high impedance input. The clamps are not located up here. They would be down somewhere on the main circuit board. These two pieces here I assume are just some kind of choke. Looks like a small ferrite bead down here. The shunt doesn't look quite as heavy duty as the one I made for the UT61. Up here you can see where they've crimped it to try to make the adjustments. Looks like this should just slide. Yep, there it goes. Huh. Big old hair. That is not mine. It's way too black to be one of my hairs. But yeah, I don't see any additional protection on the backside. It's interesting how they're using the standoffs to electrically connect the mezzanine board down to the main board. You can see this is the common point here. Runs down to this large trace. It runs over these 2 transistors that are sitting back to back. So these 2 large transistors are definitely part of the input clamp. You only see the one pair of them, and of course you have 3 PTCs, so I'd expect there to be at least 2 additional clamps like this. You know, it could be made up of these diodes down here. You can see it's got some signs of grease. Basically for the ball detent, it looks like. You can see it has 2 spring-loaded steel balls. It's nice it's sealed up like that for dust. A lot of copper in that switch though. You know, as nice as this meter looks, I'm really surprised they don't have any additional protection on it. You know, $100 meter like this. This is not at all what I would expect. Alright, so I went through a basic functional test. The meter still works fine. The next thing we're going to do is we're going to place this thing in the current mode. And we're going to attach our high voltage supply to this, and we'll remove the fuse. And let's just see if this thing can withstand, we'll call it 1200 volts. So again, we're going to be going between the amps input and the common input, and we'll just be attaching this right to the DC output of our high voltage supply. Again, this ESD gun is capable of putting out a DC voltage. There's 200 volts. You can see it's limiting it. That's all I can get out of this supply, 370 volts. So normally they would have this thing tested with a, I think they said 500 watt power supply is what they call for. Of course, this power supply is not rated for anything that high. So yeah, if we hook this thing directly up to the line, would it fail? My guess is it might. You know, when you look at this design, I don't even understand why they're connecting to this side of the fuse. You know, ideally they want to be looking at this side across the shunt, but it looks like they attach it over here. Yeah, that's just a bad design. Really, I think what we'd want to do is cut this trace and then route it over here. It'd be interesting to see the schematic for this meter. Again, you know, mechanically it looks okay, but again, electrically, I'm just saying this is pretty much a junk meter. Sad. Just do a quick check of it, make sure we didn't damage anything. Should be putting out about 2 amps. Looks fine. So as long as we have the high voltage power supply out, let's just switch this over to DC volts. And this thing should be able to read 600 volts. 350, 360. There's 500. Oh. Yeah, it looks like it overranges right at 600. You know, at 300 volts, I'd expect this thing to have another digit to it. It's a 4,000 count chipset. Let's try manually ranging it. Alright, so if we go into manual range, we can pick up that extra digit, but unfortunately when it's auto ranging, it selects the highest range. What I'd like to do next is hook this up to one of my engines and try this thing out for real. Unfortunately, that's a little more difficult than what it sounds, but what I have here is a hardware in the loop simulator that I developed a few years ago. Up here, this is a standard instrument cluster that would be on a motorcycle, and in the box below you can see I have some various potentiometers. There's switches here, some LEDs. This gives you an indication of what the engine's actually doing. In the back there's actually a ECM, and that's the real ECM that would go with this engine. So the way this kind of works is there's a circuit board inside the PC that has an FPGA on it, and then that FPGA simulates all the timing signals for the ECM. So essentially what we're doing is making the ECM think that this is actually running on a real engine. On the front of the load box I have various banana connectors. The bottom one is ground. Just use the gray for that. And then the other 3 are generic inputs. So what we can do is use that to attach our meter. So for the ground, we'll attach to the RPM minus. I'll use the 3rd one down for our RPM pickup, and the 2nd one down we'll use for our ignition. And so this is looking at the main panel of the software. You can see I have various gauges here. This is the fuel level, the coolant, the throttle position sensor, the air pressure, intake air pressure, and intake air temperature. You can see I can go ahead and turn on the power supply, and you can see the gauge cluster powers up. On the lower bar I have all my signal generators. This lower left one controls the crank speed. This is the camshaft speed. This is the output shaft speed, the clutch basket speed, and the inner hub speed. This bar selects the gear that we're in. This display is for the mile per hour, and the one beneath it is for the RPM. The ones that we're really interested in here are the injection pulse time, and that's in milliseconds, and the absolute start of injection. This is in cam degrees, the ignition dwell time in milliseconds, and the relative timing of the ignition pulse. So the meter itself will read out in RPM and the dwell time will be in milliseconds. So we'll be able to compare those 2 numbers directly with what we're seeing on the display here. This signal generator is a little more complex. You can select the torsional. On a reciprocating engine, the crank speed is not going to be constant. So as it goes through a power stroke, the piston is going to be accelerating, and as it starts to compress the air and fuel mixture, it'll be slowing down. So what you'll end up with is kind of a sinusoidal waveform, and that's what this is doing, is programming that profile. We can also control each individual cylinder. So for example, at 0 degrees, if I wanted to speed up the piston, I could put in a profile similar to this, and just on that one piston is going to be speeding up and the rest will remain constant. This is looking at some of the data coming off of the ECM. Again, because we are recording what information the ECM is providing to the fuel system, I can collect all that with this. So this is looking at the dwell time, this is the fuel pulse width, the start of injection, and this is looking at all 4 fuel injectors combined. This is for each individual cylinder, so if I want to look at the fuel timing for cylinder 1, I select the cylinder 1, this would be cylinder 2, 3, and 4. I can also compare this data with another ECM load if I wanted to. These are some of the parameters for the environment. These are some of the engine setup parameters and some of the vehicle setup parameters. So for example, your transmission gear ratios. This is our engine model. Again, we can run this simulator in closed loop mode. You can see the cluster here matches what the cluster looks like. This is our FPGA programming. I would just select FPGA program here and it would load up a new core. And the last one here selects our audio. So this simulator will actually simulate the audio coming off of the engine. So if I want to run this thing open loop, for example, I can select our flashbank here, enable the audio, and let's just put out 100 RPMs. You can see it's a very slow crank. I want to speed that up a little bit. And that's what the engine would sound like when it's starting. And you can see down on our load box, we have 8 different LEDs. The top ones are for the ignition, and the green ones are for the fuel injectors. So when the green light here is active, this means that that cylinder 1 fuel injector is actually injecting fuel. When the red is active, that's when we're charging the coil, and just at the point it goes off, that's when the ignition fires. This is our starter switch. This LED is for our fuel pump. These pots allow me to override, so I can either have these different functions driven by the computer, or I can set them to the lower switch and then I can run them manually. To go ahead and start the simulation in closed loop, I just select closed loop and I hit the starter switch. You can see it's setting the initial, it's priming the fuel system, and it's waiting for you to press the starter button. And let's look at the engine model page. And we can see the gauge cluster basically matches what we have on the real cluster. And you can see as the engine's starting to warm up, the RPM is slowly dropping. So I can go ahead and give it some throttle. Let's just go back to our main control panel. And you can see that's basically matching what our meter is showing here. For the dwell time, it's roughly 5.7 milliseconds right now. So let's just change the meter to display the dwell time as well. And here we have it. So it's currently 5.7876 milliseconds. And our RPM is in the upper right. What I'll do is I'll put the bike into gear, so we'll select first gear and we'll go ahead and give it some throttle. So here we've hit the rev limiter, and you can see we essentially shut the ignition off, but we are still applying fuel to the engine. And that's essentially to protect the engine. And that'll happen as long as the bike is either in neutral and the clutch is released, or it's in gear and I have the clutch pulled in. So what I'll do is I'll go ahead and open the throttle valve all the way. And now what I can do is release the clutch. And you can see it's on the upper rev limiter. Let's just do that one more time. So again, throw the throttle open. You can see we're on the rev limiter, and I'll go ahead and release the clutch. And you can see it go through the different shifts. There you can see it's in 5th gear. It's topped out just a little over 10,000 RPM, and that coincides with what our meter is showing. And again, you can see our ignition dwell time is roughly 1.33 milliseconds, and that's exactly what our meter is showing here. If I want to show the fuel injection time, we can go under diagnostics, and we can just set this to fuel injection. Here we can see it's roughly 9.99 or 10 milliseconds of fueling. Again, we're up on the rev limiter, so you can see it actually cutting the fuel out. We'll just bring the RPM down a little bit, and you can see it's a solid 10.5 milliseconds, which is exactly what the meter is showing. Currently you can see we're driving the engine at roughly 300 RPMs, and the dwell time is roughly 8.34 milliseconds. And again, on our meter we can see it's reading roughly 8.35 milliseconds. Another feature that this meter has is it can read this off in degrees. So that's this symbol here. So we change that to degrees, and you can see it's displaying roughly 7.2 degrees. So if we look at the diagnostic page, again we can see the dwell time is roughly 7.5 degrees, and then this is in camshaft degrees. So of course this is a 4-stroke motor, so the camshaft is spinning at half the speed of the crank. So I'm talking about camshaft degrees, I'm talking about 360 degrees of the camshaft, and that's including all 4 strokes of the engine. So if I switch this over to the fuel injection, you can see the meter is now displaying 10 degrees, and that's what we're putting out, is roughly 10.2 degrees. Let's go ahead and we'll change the RPM of this a little bit. So now you can see the injection timing is roughly 143 degrees, and that's what our meter is showing. Again, if we change this over to the dwell time, we would expect that to be 32 degrees, and that's exactly what the meter is showing us. So it appears that this function works fine in the meter as well. So this button selects the tone wheel profile. You can see I have an MSD type as well as the Hayabusa. Hayabusa is using typically a 24-1. If I were to select, for example, an MSD profile, and what's going to happen now is I try to rotate the engine, you can see that it's having trouble synchronizing with it. I mean, we're at 1300 RPM right now, and the ECM can't lock to this. Load in the standard profile and it's just fine. Alright, so let me just reduce the RPM to 500, and I'm going to enable the audio. And now what I'm going to do is enable the torsional noise. So let's just select our meter for RPM. So you can see it's currently displaying 500 RPM. And now I'm enabling the torsional noise. You can see they heavily filter this versus the display on the PC. This graph here is actually looking at the RPM coming off the engine. This is a Fourier Transform of the engine speed. So let's change the profile of the torsional noise. What I'm going to do is just give it a little notch where one cylinder drops out just a little bit. And I'll program that profile in. And you can see what that does to the Fourier Transform. Again, all the profile, the audio, everything, it's all done inside of an FPGA. There isn't any real software interaction. That's the reason that this model can run real time, is because basically it's all done in hardware. Again, this system isn't anything that you could go out and buy. This was custom made by myself. So you'd have to look at some companies like D-Space or something if you were trying to buy something like this off the shelf. I know National Instruments offers some kind of FPGA support. but I think it basically is a wrapper. So the way it works is you're kind of using LabVIEW still, and you have to work within the constraints of what they're allowing you to do with the libraries for LabVIEW. That's not at all what I'm doing here. Again, this is a custom board as well that's in the PC, and I'm just writing the software directly inside of the Alternator tools, and that's all in VHDL. And essentially I'm just communicating to that FPGA through the PCI bus. Same with like the slew rate control function. This is all done in hardware. So if I wanted to ramp faster, it's completely hardware. There's no software involved. Some of the interesting things you can do with a simulator, of course I could run the motor backwards. That's not something you could easily do in a real engine. Here you can see I can also create like a chipped waveform. So for example, if the tone wheel got a cracked tooth or something, I can change that as well. So if I wanted to change the rotation of the motor, I can easily do that right here. If I fire this trigger, this is going to cause me to blank out a tooth. You can see how it loses track. Let's just do continuous. You can see how the motor misses a beat every now and then now. I think the next thing I'd like to do is try this on a different ignition system. Unfortunately, again, we did not receive the inductive pickup with this. A while back, you may remember I bought these two Fluke 97s, and these came with all the accessories. So there were two different kind of inductive clamps. There's this one here that connects up to the two banana jacks. I'm not sure if this is going to be compatible with this meter or not. You can see the small ferrite in here. There's the coil. It says spark plug, plus minus, and Fluke. Alright, so this is looking at one of my test jigs. Here you can see we've got the clamp. You can see I have various ignition coils. This is a pressurized block. See, it has a window in here, and I have 4 spark plugs mounted to this. And there's a pressure gauge here. And then off to the left here, this is a tank of nitrogen, and I've got a regulator on here. And I can use this to control the pressure inside of this cavity. There's a small circuit board down here that's connected to Ethernet, and that's got an FPGA on it that'll generate all the waveforms. And then there's a MSD MC4 ignition mounted under here as well. I've also made up other harnesses so I can run different ignitions with this thing. The reason I want to try this with the MSD is, of course, that's a multi-spark discharge ignition. So what that means is normally what will happen is you'll get a single event or a single ignition cycle for one combustion stroke. With this type of ignition, you'll actually get multiple sparks. So that way, if the flame were to blow out, it can actually reignite. So let's just go ahead and we'll turn this thing on and see if we can get any kind of RPM out of it at all. And you can see we are outputting right now roughly 700 RPM. And you can see what this is doing to our meter. Let's just try changing the trigger level. Can't seem to pick it up there. You can see it's reading 11,800 RPM right now. Of course, we're running nowhere near that. We're at 690. You can see the ignition is running. See how it resets the meter? This is the kind of shit that you got going on in automotive. You would think that the meter would be pretty much immune to this, but obviously it's not. Obviously the electronics that are driving the ignition are not having any trouble with this. Let's go ahead and take the RPM up, and what I'll do is connect up this spark plug here. So even here you can see it's not stable. This is all the way up at 6,200 RPM. Even if I move the meter away from the test jig, you can see it's wandering all over the place. Well, that's unfortunate. What I was going to do was pressurize this chamber if the meter were at least stable, but what will happen is you of course increase the pressure. That's going to increase the breakdown voltage of the plugs. Of course that'll put more strain on the ignition system. Of course that's going to also emit more RF when I do that, but you can see the meter just can't even make it with the setup that I've got right here now. Alright, so obviously our All-Sun EM135 has a lot of issues with the ignition noise coming off this MSD. I thought what I'd do is hook up our Bryman BM869S. Now of course this cannot read RPM, but it can read frequency. So what I'm going to do is just set the RPM for 6,000. So 6,000 divided by 60 should give us 100 Hertz on this thing when I turn on our ignition. So let's just fire that thing up and see what happens. So look at that, it's rock solid. Let's try moving it around a little bit. See that? It's the exact same pickup, connected on the same wire. I actually didn't even disconnect this at all, but if I just detach it real quick, and we can try it on a different wire. Shouldn't make any difference at all, I wouldn't imagine. There you go, 100 Hertz. Alright, so just like before, you can see I have a spark plug over here, and I'm just grounding this to the plate. I've just got a piece of circuit board here that the 2 meters are setting on. You can see how this thing just keeps resetting. And it's pretty bad. I mean, there's absolutely nothing attached to that meter. It's just turned on. And that in itself is enough RF right there. Just having that wire sitting there cause this thing to reset. That's pretty bad. And for fun, you can see I've got the little sun test out. See this? It airs right out and it turns off. See the backlight's kind of on. You can see I've got Dave's EEV blog rebranded BM235. Oh, see, it just went through a reset as well. I don't know if you can see this, but it's definitely flickering in the backlight. Yeah, the keyboard isn't even working. So it looks like the BM235 is a little more susceptible to the emissions than what the BM869S was. So overall my impression of this meter is pretty poor. So for starts, the fact that they didn't have the manual available online, again, that would have saved me a lot of trouble, because I don't think I would have purchased this meter just based on the specifications that are in the manual. The only thing I don't like about their online website is I think they're deceptive. The fact that they're calling out that this is basically 100,000 counts, and it is. I guess you could display that upper digit if you're in RPM mode, but the reality is this is a 4,000 count meter. That should have been disclosed right on the website if you're not going to have the manual. There's no shielding inside of this meter whatsoever, and what you saw is when this thing was near any of the RF that was coming off of that ignition system, the meter was continually resetting. When I was working in the automotive industry and doing design work, we would test at 100 volts per meter. Typically for commercial products, you're going to test at 3 volts per meter, and industrial products are typically 10 volts per meter. So the industry knows that the automotive is typically a harsh environment. You would think that these meters, if you're going to charge a premium for them, would be designed for that. You know, with this thing not having any shielding in it, I don't know if this would even pass at 3 volts per meter. Another one of my big concerns with the meter is when I had it attached to a 260 volt power supply. You saw where it was basically resetting. The display would go blank. Sometimes the backlight would become active. It was very similar to what we were seeing with the RF susceptibility. So I don't know what's causing that. It doesn't appear again to be a mechanical problem with it. I think it's something in the electrical design. When we had it apart, you could see again there were no MOVs. The most I saw were a couple of transistors down here back to back in the 3 PTCs. You know, if I hook this thing up to our transient generator, I'm sure I would damage this at a fairly low level. For it being a $100 meter, I would expect this thing to do true RMS. And it's an averaging type meter. Again, this meter being 4,000 count, I demonstrated where I applied 300 volts and you only saw the 3 digits. Basically, it looks like the auto ranging has not been optimized, so you don't always get all the digits that the meter actually claims it has. So personally, I think for the $100, it's a waste of money. This isn't something I would ever recommend for automotive use. I think a meter like this that would have similar features could actually be useful in automotive. So if you've used other meters like this in the field that have similar features that you've liked, go ahead and post about those in the comments. I'd be interested in hearing your thoughts on it. Well, until the next meter. Later.